right click on the desktop, create new folder. So I'm doing part A, so let me type part A, create. So within this I'll take up the very first experiment, which is an inverter. I'll create one more folder to create the inverter, otherwise you can do in the same folder, no issues. Next, right click, open terminal. In the open terminal I need to give the command csh to invoke the virtues. So csh source home install cshrc virtuoso, enter. Wait for a while. Here is your virtuoso window. Go to file, new, library, create your own library. Say I'll give lvda, which attach to the existing library. I'll choose dpdk 180 as my mother library. Next, go to file, new, cell view. In the created library lvda, I'm going to create a new cell which is called as inverter. So here is the inverter. To the inverter, to draw the inverter, that is to create the schematic, I'll go with add instance, browse, there go to GPDK 180. I need both NMOS and PMOS, so I'll take NMOS. I'll retain the length and width as it is. So NMOS. Next, browse for PMOS. Close. I'll retain the width and length as it is. Keep it there. Then go with the wire. So here you have the narrow wire. Otherwise, press W on the keyboard. You will get the wire. Make the connection for the inverter, connect, connect the substrates, connect the ground, and leave the terminals. Next is making or creating the pin. To create the pin, click on create pin on the desktop or just press P on the keyboard. So I need A space VDD space VSS. These are all the inputs. So I'll take the inputs, place one after the other, A, then rotate. You can see the next one is VDD, the next one is VSS, rotate and place. And again pin Y, and the direction is output. So change the direction to output and place it here. So once it is done, check and save. Go to file, go to create, cell view, from cell view. This is the step to create the symbol. So left pin let it be A, right pin let it be Y, bottom VSS, top VDD, and create OK. So this is a symbol. It is completely user defined. You can define your symbol here. You can draw the inverter. You can change the labels and make the labels accordingly. So because I'm doing the inverter, I'll change it as NOT gate. Instance name also I can give it. Let me delete it for time being. So this I can delete it. This is how your inverter looks. If you want, you can also delete the red line. So it is completely user dependent. If you wish, you can create it. Otherwise, use it as it is. Now minimize it. Go back to the window. There, go to file, new, inverter. I want to test the inverter in its functionality. So I'll give inverter test. Click on OK. To test the inverter, I have to invoke the same symbol what I have created there. So go to LVDA, inverter. So you have the symbol here. Close, hide. Here is the symbol. Next, I need to give the supply, input, and connect the outputs. For that, go to add instance, browse, go to the library, analog library, there VDC, close. The DC voltage I need here is 1.8 volts. Just type 1.8 and click. You will get volt as it is. Do not try to type the voltage or other units, standard units here. So I will rotate it R 3 times, that is press R on the keyboard and place it here so that your plus, so this positive terminal is very near to your VDD. Next, add instance, browse, V pulse. I need a pulse to check the working of inverter. For that, let the voltage 0 be 0 or voltage 1 be 0. Second voltage, let it be 1.8 volt. Period, let me have 20 nanoseconds. Delay time, let it be 0. Rise time 1 pico. Fall time 1 pico. Pulse width 10 nano. Okay, these are the parameters. Click on hide. Place it here. Next, add instance, browse for a capacitor for a load. So capacitor, I am using it as load. Capacitor, close. The value, I will choose it to be 100 femtofarad. So 100 small f. Place it here. Next, at the last, I need ground. Go to browse and GND. Ground, here is the ground. Close, hide. So I will connect the ground wherever it is necessary. Okay. Now make the wired connections using narrow wire or press W on the keyboard. So here is the connections. Connections are done. Check and save. Next step, go to launch ADEL. Here is my ADEL window. The very first step here is go to setup and model libraries. So make sure that 180 nanometer model spectre GPDK SCS file is selected and change the section to NN and click on OK. So if at all, if you find any other library files, uncheck them and only allow this file or this GPDK to be active. Next, go to analysis, choose analysis. In the choose analysis, first is transient analysis. I will take 80 nanometer moderate DC analysis. I will choose component parameter, select component. I need to select the input here. So this is the input, DC input. So I have taken the DC input as V1. Start time, let it be 0. Stop time, let it be 1.8. And why 1.8? This is the maximum voltage what we have taken. I will take linear scale, step size, let it be 0.01 and click on OK. So we forgot one more step. So here I need to label these two wires, that I need to do. A, comma, Y, hide. So this is A and this is Y. Go back to ADEL step. Here simulation and check and save. Go back, output to be plotted, select on design. I need to plot A and Y, so I am selecting these two. Come back and just click on run. Okay. This is a simulation what we are getting. Just split the screen, you can see this. So this is a DC response where the output is moving high, or it is having the high value whenever the input is low. After that there is a fall and it goes, or it takes the value which is very near to 0. Next, coming to the transient analysis. So this is a transient analysis. In the transient analysis, we can see the A is high and the output is low. Whenever the input is low, output is high. This is the functionality of inverter. I need to calculate the delay time. To calculate the delay time, just press on this calculator button here. So this is a calculator button. Especially I need to concentrate on this function panel. So function panel, just click on the delay here. So and select wave and clip, you turn it off. Okay. So you just turn it off the clip. I don't want a stack window, remove that. Signal 1 should always be input. So just click on signal 1, go to the virtual window or this Virtuoso visualization window. There select A. Signal to, click there. Manually go to the waveform window, click Y. So you can see A and Y are selected. Next, threshold value I will take 0.75. Even for this I will take the threshold value as 0.75. Edge number 2 or 3. You can select either 2 or 3. So if you are selecting 2 here, let you also select the other also 2 or 3 or 3. Now, type of edge, I should have a rising edge in the first step. Here I should take falling step. Okay. So that's all. These are all the changes I make, and click on apply. So once it is applied, you can see a command has been registered here. Next, click on evaluate the buffer. So you can see this is the time taken for the signal to propagate from high to low. Now let me calculate the other way. So for that, click on the calculator button here so that it remains intact. Now falling edge to rising edge, and again apply and calculate. So you have the other value, which is time required for the propagation from low to high, is given here. Now take the average of these two to calculate the delay time TD. So simple calculation, close this, and your waveforms are done. So ADEL is done. Just close it. Before closing it, it asks for you to save it, close it. Come back to the inverter window. The next step is to create a layout. To create a layout, go to Launch, Layout, Excel, Create New, and click on OK. So here is your layout window, Excel window. Go to connectivity, generate all from source, and OK. Here is your NMOS, PMOS, and the other 4 pins ready. Now zoom out, click on S on the keyboard to stretch the boundary box. I need a little spacious design, so stretch the boundary box. Go to connectivity back, generate, place as in schematic so that it is placed properly on the window. Next, go to connectivity back, incomplete nets, show and hide all incomplete nets. So it will show us how the connection should be done. Now use Shift F on the keyboard to see the other details on your screen. Okay, here is your rat lines. Next, place the MOS transistors properly so that your connections are legible and also they are separated according to the lambda rules. So this is how I separate them. And the next step is I have to detach the body, that is substrate part, from this transistor. For that, select any one of the transistor, press Q, it goes to the properties. One second. Okay, Q, properties. In that, go for parameter. Body type I will take detached so that you can see the bulk connected here. The same I will repeat for the NMOS. Depending on the design, I can select the body type to be attached or it can be integrated. Now press P on the keyboard so that you can see the cursor has changed. So it's indicating that you can make the connection or you can extend it. So carefully connect all the parameters or all the layers with each other according to the rat lines what they have indicated. And yes, okay. So here you can see it is connected to VDD. VDD connection done. Come down. Yes. Yes, all the connections are done. Fit, go to, sorry, close it. Okay, save the file, go to file, save it. Now go to Ashura Technology. So browse for the technology file, double click on these two dots until you find install, then go to Foundry, Analog 180 nanometer, Ashura tech.lib and click on OK. Next step is go to Ashura, run DRC. Here technology define it to be GPDK 180, rest all remains usual and click on OK. There is a DRC error here. There is a layout error here. I have not attached this, so I need to attach it. To attach that, click on this window where you get via, create via. So via should be from metal 1 to poly, hide and place it. So this was missing and it is done. Again repeat the DRC check, design tool check. Yes, overwrite. No DRC error found. Let me check for the layout versus schematic error. Define the library to be GPDK 180 and click on OK. So it is in progress. So there is no mismatch. Click on yes. Wait for the additional windows. Okay. So now no mismatch. Therefore I will close the other window. Done. Now is to extract the parasitic capacitances. For that, go to Ashura, run Quantus QRC. Quantus QRC. In this, select the technology GPDK 180. Go to the next tab, which is extraction tab. There I should select RC. I need both resistor and capacitors, and the rest all remain same except the reference node. What is the reference node I am taking? VSS. Select that VSS and click on OK. So wait for a while. So QRC is completed successfully. Now how to see the generated QRC file? Go back to your Virtuoso window. Okay, go back to your log file. There go to Tools, Library Manager. In the Library Manager, go to the library which I have created and just click on the inverter. You can see AB extracted is already attached here. Double click on that. And here is your AB extraction. So you can zoom for different parasitic resistances and capacitance. Now press Shift F on the keyboard to see the different structures, that is physical structures that are present here. Okay, so this is your parasitic extraction. I will close the window. Yes, next is I have to simulate, or I have to use this parasitic capacitance and test whether it is working properly or not. So for that, click on inverter test. So this is a test symbol, right? Click on that. Go to File, New, Cell View. Just clicking on that you have to do. Next, go back here, select the layout view to configured view. Okay, so configure view and click on OK. So here in the new configuration, select the user template. I need to select the user template as a spec tray and apply OK. View should be schematic view and click on OK. So this is the hierarchy or configuration file where I need this to be seen as a tree view because this is the inverter schematic. I'll find it here and right click on that, set the instance as AV extracted. Okay, so it makes sure that whatever the AV extraction we have done, it is completely merged into your first file. Now click on open. So here is your AV extracted file. Just double click on that. You can see the AV extraction again. So this is your AV extraction. Go back. Yes, here, and click on open. You will come back to the previous window. So nothing much. Go to launch ADEL. So before closing the previous window, I have saved the state. Therefore, I can reopen the same state. Okay, so I can reopen the same state. Yes, and just click on run. So we got the outputs again. Yes, this is your DC response, this is the transient response. I'll close the DC response for time being because I have analysis to make with your transient response. Click on the calculator button, repeat the same step. So I'll delete all these parameters. I don't want all these things right now. Okay, signal 1. Delete it. Okay, signal 1, click it, go to the waveform. Signal 1 is always input. Signal 2, go to the waveform, click on output. Done. Now all other parameters are same. Only thing is here first step I need to change rising to falling and apply, calculate. So you got the value. Click on the calculator. Next, go back, falling to rising. Here again apply and calculate. So we can clearly see that whatever the values we are getting here, it is very similar, or not very similar, it is exactly the same what we got for the previous one. So this is how you calculate a delay and we generate the transient response and the DC response for a layout.